Alright, in this video I'm going to start talking about how to determine the pH of a weak base solution. So here I'm asking what is the pH of 20 milliliters of a 0.25 molar pyridine solution. Pyridine is an organic base. This is what its Lewis structure looks like. At every vertex there's a carbon atom, and at that carbon atom are enough hydrogen atoms to fulfill its octet. So it's a shorthand way of drawing what pyridine looks like. So this is weak base pyridine, and throughout the course of this video I'm just going to abbreviate it as R3N, and N has this lone pair of electrons on it. So first, how can we determine that this is a base? Well, I gave you a KB, so that's a sign there. But also, remember, bases pull protons off of acids. Acids donate protons. If we look at this structure of pyridine, there are no protons for it to donate anywhere. So pyridine is going to be a base. This lone pair of electrons is going to be able to pull hydrogens off of acids. So let's get started and determine what is the pH of the solution. We're going to put pyridine, R3N generically, into water. We've already determined that it is a base. It's going to pull protons off. So let's predict the products of this reaction. When R3N pulls a proton off of water, you're going to get R3NH+. That is the conjugate acid of pyridine R3N. When water donates its proton to pyridine, you're left with hydroxide. When you're determining the pH of a weak base like this, you're going to need an ICE table, an equilibrium table. So the initial concentration of our R3N, our pyridine, is 0.25 molar. We don't really care about the water concentration. It doesn't appear in the KB expression. It's kind of a pure liquid. It doesn't really affect our pH, so we don't really care what's going on with water. Our initial concentration of conjugate acid, R3NH, is 0. And our initial concentration of hydroxide is also 0. In the change, the equilibrium is going to shift to the right because we have no products. So at equilibrium, we will have some products. So the equilibrium is going to shift to the right. In that shift, we're going to subtract x because the coefficient here is 1. We're going to gain x for conjugate base, R3NH, because the coefficient is 1. And we're going to gain x here for hydroxide as well because the coefficient is 1. So that means that at equilibrium, we have a concentration of R3N of 0.25 minus x. We don't care about water. At equilibrium, we have x concentration of conjugate acid, R3NH, and we have x concentration of hydroxide. Let's talk about the KB expression. So KB is very similar to any other equilibrium constant, in which it's the products over the reactants, and don't forget they're raised to their orders. So the KB expression here is equal to the concentration of conjugate acid, R3NH, times the concentration of hydroxide, both to the first power, again because their coefficient is 1, divided by the concentration of the base, R3N, also to the first power, because its coefficient is 1. Water is already taken care of in the KB expression, so we don't have to worry about water here. So now we're ready to start plugging things into this KB expression to solve for x, which will give us our concentration of hydroxide. So KB is 1.7 times 10 to the minus 9th. That'll be equal to x squared divided by 0.25. We're making an assumption here. To just simplify the math, we're assuming that the equilibrium isn't going to shift too far to the right, and at equilibrium the concentration of weak base pyridine is still going to be about 0.25 molar. So that's why we have 0.25 down here in our equilibrium constant expression. So then we're going to solve for x. X is equal to 2.06 times 10 to the minus 5. And whenever you make an assumption that the change in x is going to be negligible, you want to check to make sure that that assumption is valid. You check to make sure that assumption is valid by putting x, 2.06 times 10 to the minus 5, divided by your initial concentration, 0.25 times 100. This tells me that our change in X is only 0.00824% of our initial concentration. That means that our assumption is valid. Usually we say if it's less than 5%, then our assumption is valid. So now let's analyze what we have and see if we can get to what the pH is. X is equal to the equilibrium concentration of hydroxide. Since we have strong base hydroxide in the solution, we can use that directly to determine our pH. So the concentration of hydroxide is equal to 2.06 times 10 to the minus 5. That means that our pOH is equal to the negative log of the hydroxide concentration, 2.06 times 10 to the minus 5. This gives us a pOH of 4.69, and the pH is 14 minus the pOH, giving us a pH of 9.31. And it makes sense, because this is a weak base, so we should have a basic pH.